All right. So now I would like to introduce some new articles which are very important because the hedge funds should have some targets. One of them is robust portfolio. It means that, for example, if your covariance matrix has some parameters and they are not certain, so you should take into considerations the robustness of your portfolio. So not only your covariance parameters, but also your expected returns, because you have predicted them. So everything is just uncertain. And the other point I would like to mention is multi-moment. As I said in my previous lectures, that we really take into considerations mu, the mean, the expected return, and sigma, which is the standard deviation of your portfolio. But we often forget that many hedge funds, their portfolio is highly nonlinear. They use options for hedging, and so they need higher moments such as skewness, which is the third order moment, and also kurtosis. Of course, skewness is much more important because it is expectation of, it's the second moment, and so that's much more important. And multi-factor, I explained in my previous lectures, when we talk about multi-factor, we can take into consideration some bonds and different asset classes. It's not just about equity, but you can also talk about real estate, bond, derivatives, and many more. So it's a multi-asset investment. So we should also consider transaction costs. So when the frequency of rebalancing is too high, so your cost will go up very dramatically. So I introduced this great article by Professor Kirstens and his friends. So he introduced shortage function. Of course, it's not new. It is it is written in a book for Lohenberger in optimization. So he talks about skewness. He adds skewness to your efficient frontier. So your efficient frontier is not only 2D, so it's but also it is highly 3. It's a 3D efficient frontier, and so because our investors are interested in positive skewness. It's when a positive skewness is a low probability of large negative returns, as it occurs in financial markets and especially equity markets. So when you talk about sigma, you should know that it is only valid when your rebalancing is very fast. You do it in a high frequency. But when your portfolio is very nonlinear and you don't do that, the frequency of rebalancing is not that much, then you should take into consideration skewness. So as the dimensionality of the portfolio selection problem increases, it becomes more difficult to develop a geometric interpretation and to select the most preferred. We will see that how this is this 3D efficient frontier. So this is the skewness, this is the mean and variance. So he introduced the shortage function, which is a perfect representation of multidimensional choice sets and can position any point relative to the boundary. So this is the expected return, variance, and skewness. This is just general. So you should note that because our matrix covariance matrix or even skewness, all of them are symmetric. So we only need the upper part. So we only need the upper part of your matrix. That's why the number of parameters is reduced. Or even is in skewness, it is reduced. So we go from 2D to 3D or even higher dimension if we add kurtoses. And so he tried to formulate it using a shortage function, which is the supremum of all delta, such that when you go through that vector, you go inside the dr set. And so he formulated like this, that you want to maximize delta subject to three constraints, which are related to expected return, variance, and skewness. And the last one is we always do that because the sum of your weights should equal to 1 in the portfolio selection. And so this is a kind of optimization problem which is very hard because we can do it with cubic programming, of course, but if you and this is like this because in general it's a non-convex optimization, so it's really hard. I mean, mathematicians really like to convert a non-convex problem to a convex problem because, in general, it is globally. For example, if your optimization is locally convergent to a point, then it is globally optimum as well. So we can think about portfolio optimization as if we just use, because it's a positive definite matrix, because the covariance matrix is positive definite matrix and it's symmetric, so we can decompose it as a Cholesky decomposition. And if you do that, you can easily see that it's just the we have written a kind of constraint as intersection of a cone with some affine spaces, and that's why this is the second order cone programming, and you can solve it with any SOCP solver. So as SOCP solver, you can use interior points that I will be talking about it, and so let's talk about a cone. What do I mean by cone? This is the formula of elliptical cone. So if A is equal to B and is equal to 1, then it's just a circular cone. It's simple normal cone, and you can write that as well. I mean, so it's related to. So if you want to also learn Greek philosophy, you can start with nature. You can start with these shapes. You see all of these shapes in nature. So intersection of affine space with a cone can give you all sorts of geometric shapes. So our methodology is that we use the expected return of CAPM or anything you like, multifactor returns, anything. And then you use either quadratic programming, or if you're really lucky, you can handle it with second order cone programming, and then you solve it. So I introduced 2 great books. This is for basic, it's very basic if you have just started, and if you're very advanced, you can have a look at this book as well. So when we talk about dual variables or Lagrange multiplier vectors, we have some dual variables, and we want to minimize subject to some inequality and some equality constraints. So the problem is that when we have inequality, so we have to use some kind of tricks such as slack variables to make it like equality, and then solve it with Newton solvers. And I introduced a Lagrange dual function here because if you work on that, you will notice that it could be a very good lower bound. We have proved it here in this book, in the last chapter, that it could be a lower bound for your optimization, and it shows you how much optimal your suboptimal point is and how much close you are to the target. And so we don't see that very much in mathematics. So in few conditions, such as when we have a convex objective function and we have some convexity conditions, then we can come up to such nice stopping criterions. Because, if the gap between the primal and dual objective is reduced, you're going very, very close to the target. And so your suboptimal point is, you can say, it's a global optimal point. And that's really nice. So you can solve this, but just go through the KKT conditions as we do for any optimization, and just solve it. And so the trick of logarithmic barrier function, which is just one of the barrier functions, and barrier functions is just one of the methods of interior point to solve such equations, such optimization problems. You will notice that this log barrier function that I will explain here, this one, is just an approximation. It is just an approximation of your indicator. I mean, this indicator. And so all of this is just about converting an inequality to equality, so that we can solve with traditional, easy to solve Newton equations, Newton solvers. And so we have a primal feasibility in KKT condition, and we have a stationarity conditions. So lambda is here, and V is here. These are the dual variables, as I mentioned. And when you interpret, you see that this one and this one is completely the same, except this one. So if t goes to infinity, it reduces to our simple KKT conditions. And t, so we introduce t, we increase t from 0 to infinity to make it converge. So for example, this one is t is equal to 1. This one is for t is equal to 2. And up to when t is increased, and you get the optimal point is here. And that's because we have proved here that if t goes to infinity, this gap goes to 0. It goes to 0, and your suboptimal point is just the optimal point, using just simple proof. So we can use this t in the barrier method, in the barrier algorithm, which was originally from 1960, and some people say path following method. And you keep increasing t until convergence, and you have a great stopping criterion, and we have proved that, because we want to reduce the gap. And so you solve this using Newton equation. This is for 1D equations. For higher dimension, you can do Newton method. But what is the step that we need? We use the KKT conditions, and I will show why this is TH and why this is TG. So as I said, this is just the KKT conditions, and if you just approximate this with some Taylor approximation around x, and don't forget that nu is different from v, although they are very similar Greek variables. So if you work on this, you understand that if you do the Taylor approximation, you get these steps that you need for Newton steps, both for your x, your primal, and your dual variable. So we have understood that this holds. We go back, so we have proved that this matrix is true, and we just give it to a solver, the Newton solver, and that's it. You get delta x and v, and if you just go through that, and you will converge at some point. And this graph shows that as a number of Newton iterations increases, you have a lower duality gap, and your global optimal point is very close to your suboptimal point at that moment. But the sensitivity is just dependent on the mu variable.